Okay, now this is getting recorded. So we're still going to continue with normal distribution. And I was discussing standard normal yesterday. Uh, Samiksha, this is getting recorded right now and this is going to go on YouTube. So I will address this question after we stop recording. So only academic issues will be discussed while the call is recorded.
Excuse me, sir.
Yes,
Sir, I have a doubt regarding the shape of the normal distribution. Sir, in that one is extremely concentrated and the other is a well-rounded shape.
yes.
So, how do we identify the variance, the magnitude of variance from that? I couldn't understand that portion in the previous lecture.
Okay, I'll address that. Any other doubt from the last class? Okay, so in the course of today's class, I'll address this one, and if you have any other uh, question, so that one is okay. Now, if x follows normal distribution with mean denoted by mu of x and variance denoted by sigma square of x, and we denote another random variable which is a linear transformation of our original random variable x as mu of x divided by sigma of x. Say that z also will follow normal distribution, and this will be a particular type of normal distribution. This will have the parameters mu equal to 0 and sigma is equal to 1, and we call z a standard normal variable. If we want the probability that the random variable x takes on values between a and b with b greater than a, we can transform this as follows. So we can subtract the mean and divide this by standard deviation. I will have to do this across the inequality. Okay, so these two are equivalent. Now, in the middle, what we have is a standard normal variable z. Now, if we have the parameters of our original random variable x available, that is mu and sigma x, and if we have these values a and b, this will be a numerical value and this will be a numerical value. Then this problem gets transformed on the axis of standard normal, which is going to look like this. Centered on mean 0 would have a variance of 1. Then so I am taking arbitrary values here. This can be a minus mu of x by sigma of f, sigma of x. This can be b minus mu of x by sigma of x. We can just take a look at the cumulative standard normal table and get this. So we'll use this function. Okay, this is not phi in my handwriting. My handwriting phi is this. Okay, I'm just picking this up from the text, so they have this bold version. This is for cumulative distribution function of standard normal variable. Okay, now let's use colors. This area would be this entire region, and this area would be this one. So we'll find the area under the curve between these two values. Is this point okay? Okay, so in terms of diagrams, I had already explained in the last class. In terms of algebra, this is what it is. And if we have this inequality, probability that the random variable takes on value less than a, it's the same as, uh, let me insert one more expression. Probability z takes on a value less than a minus mu of x by sigma of x, which is this. Probability x greater than equal to b is probability z is greater than b minus mu of x by sigma of x. This is 1 minus. Okay. Any problems till here? All right. Now let me address the question. And let's use which color? Let's use blue. So we can have these combinations. Arbitrarily, let's take both the values as A. So in panel 1, we have a normal distribution centered on mean A is A. And in the right panel, panel 2, we have this. Now I will claim that the variance here is variance in 1 is less than variance in panel 2. That is all that we can see. What will be the value of the variance? I've not gone into that yet. Okay, the only thing we can make out is if the variance is greater or smaller. So we have these two. We can have various combinations. A here, B here. So in panel 3 and 4, what I've tried to do is I've tried to keep the variance same here. Mean in 3 is less than mean in 4. Variance I've tried to keep similar. Now, does this answer your query? We don't know the exact values of means and variance. They are arbitrary. We can just compare their magnitudes with the information that we have right now. Is this fine?
So how did we make out for the mean?
Mean, because I have used the same notation A and A. So 1 and 2, A is same. Mean is right under the peak. If it's the same notation, that means it's same. In 3 and 4, we have positive here and negative here. As we move to the right, the value on horizontal axis increases. So the mean of the distribution in panel 3 is A. That's to the left of B. So mean in panel 3 is less than mean in panel 4. Mean in panel 4 is B. Okay, because A is to the left of B on the horizontal axis. That's how we know. Okay.
Okay, sir.
All right. Now let's move to percentiles. First of the standard normal distribution. Okay, we just have to look at the table. Now, please take a look at the table. This is table A.3 on page A6 and A7. Please open that up. Let me know once you've opened up the table. Okay, so this is how this table has to be read. Now, this is a cumulative table. So you see the value 0.0. This is the first row on the section of the table which is on page A7. Okay, so this is how it looks. You have Z here is written 0.0 here and 0.0 here. This is 0.50. That means to the left of 0.0 plus 0.0. So you have it like this. 0.504, 0.508 is how it is read. This value plus this value. Okay, that we locate on the horizontal axis. 0.0 plus 0.0 is 0.0. To the left of this area is 0.5. Okay. Now, if we add 0.01 to 0.0, okay, so just to the right of it, you'll have 0.01. To the left of this line, the area is 0.504. So as we move to the right, the area continues to increase. This is how the table has to be read. Okay. Now, if we want to locate a percentile, let's say I want the 99th percentile. What do I have to do? I have to locate the value 0.9900 in the table. Okay, where would that value be? Just scan the table. So that value is between in the row with label 2.3 and the column with 0.03. This is where it is. 0.03 and 2.3. Here you have 0.9901. Can you locate it? Let me write it slightly more clearly. 0.9901. Okay, so from this we can read that 2.33 is the value to the left of which the area is 0.9901. Okay, that is the closest value that we have, that is closest value to 0.99. Is this clear? How do we locate the percentile for a standard normal distribution? Yes, no, maybe.
Yes, sir.
Okay, so now let's move percentile of an arbitrary normal distribution. So this is an arbitrary normal distribution. To the right of it, I am drawing standard normal distribution. Okay, so we have x here, f of x here. What happened? Can
So
you
your
still see the screen?
no,
No,
sir, your
sir.
screen is not.
क्या हुआ? Okay, give me a moment. Okay, Even Meets is not cooperating today. Members were facing problem even in the meeting. All right. Now, if we want to find the percentile of an arbitrary normal distribution, then, like I've already said, there would be correspondence in the points on the horizontal axis between any arbitrary normal distribution and the standard normal. Okay. All we have to do is find the percentile here. Okay. Let's say this is the 99th percentile. Then we look for the corresponding value here, and we will be able to find our percentile. Okay, so like we know that for 99th percentile this value is 2.33 for standard normal. All we have to do is locate the corresponding value of 2.23 on the axis of our arbitrary normal distribution in terms. Okay, let me also write the expression here. Okay, I'm writing this in sentence. Okay, how do we do that? We have z defined as this. Just invert this around. So x will be mu of x plus z into sigma of x. Uh, Percentiles are z values. So you just put 100 into pth percentile for standard normal, distribution into sigma of x. Whatever comes out of this expression would be 100 into pth percentile for our arbitrary normal distribution with mean equal to mu of x and standard deviation equal to sigma of x. All right. Any problem still here? Okay, let's proceed to another section, which is normal distribution and discrete populations. Okay, many discrete populations can be approximated by a normal distribution. So we'll take an example of binomial distribution. Let me also write in sentence. Then we move to approximating the binomial distribution.
Sir, could you please scroll up a little for once?
More?
No, sir, that's it.
Mm. Okay. Hmm. Let's consider a particular binomial experiment with sample size equal to 20 and probability of success of the random variable. Oh, sorry, probability of success of a particular trial equal to 0.6. So we have probability of failure at 0.4. Okay, the mean of the binomial distribution then is n into p, which comes out to be 12, and the standard deviation is square root of mean to probability of success of a trial to probability of failure of a trial. This will come out to be 0.219. Okay. All right. So the probability histogram of this distribution is going to look something like this. Just above 12, have this, and then we continue to come down this way. So this is slightly skewed towards the right because the probability of success is greater than 0.5. Now, if we plot, let me use another color. Okay, so this is a normal curve with mean is equal to 12 and standard deviation is equal to 2.19. So we see here that it reasonably approximates this. Now, because I've drawn it by hand, so obviously there will be that bit of error as well. But if we ask a software to do it, it'll be pretty close. Now, what are the approximation errors? Okay, because this is just approximating. Area under the curve, this brown curve has to be 1 because it's a density function. Now, these rectangles that we have drawn for the histogram, area of every rectangle, area of all the rectangles sum together, that will also be 1, because you see here the width of every rectangle is 1. So width multiplied by the probability, which is the height, will have the area, and if we sum across, that will also be 1. Now the issue is these red portions are those pieces which are under the normal curve, but they're not part of our histogram for the binomial distribution. The green ones are not under the normal curve, but they are part of the histogram for binomial distribution. Okay, on the net, if uh, they cancel out each other to the extent that the red areas and the green areas cancel out each other, we have a good approximation. Okay, if we have a binomial distribution which is more skewed, then we'll have the case where uh, some area is going to dominate the other, either the red one dominating the green one or the green one dominating the red one. Then we have more approximation, a slightly higher level of approximation error. Okay, is this point fine? Yeah, I don't see anyone raising an issue. Rishika, I missed your comment. Okay, if you have a problem, you can let me know. Otherwise, I'm assuming that this was a positive response. Okay. Then there is something called continuity correction that we have to do once we use a normal distribution to approximate a discrete distribution. For that, let me just zoom in to this diagram. So we have 12 here, 13, 14, 15, 16, 11, 10, and 9. Okay, this goes on. I've just zoomed in. What if we want probability x is equal to 10 for binomial random variable? Okay, what would that be? Let me just 8, 7. This is the probability that we're looking for. Okay, because it's a discrete distribution, then there would be a positive probability or non-zero probability corresponding to the value that the random variable takes. Okay, now on top of this, if we use this distribution, then what do we have to do? to find a correct or closest possible approximate answer. Let's also write this, but this numerically would be, this would be x takes on value 10 with the sample size being 20 and probability of success being 0.6. So this is n, this is p, two parameters of a binomial distribution. Uppercase B here means that this is a cumulative binomial distribution. Okay, so what we're doing is we are subtracting the probability that the random variable takes on value 10 or less, is subtracting from this probability the probability that the random variable takes on values 9 or less, and we'll have the probability that the random variable takes on value 10. This will come out to be 0.117. Okay, now we have here 10.5 and 9.5, these two. If I want to use the normal distribution, I will have this area as the closest possible. Red is not the right color. For this, let's use blue. Okay, so we will be including this red area that we should not, and we would be excluding this green area that we had included if we use binomial. Okay, now the issue here is 9.5 and 10.5. This is what we have to do. We have to find the probability that the random variable takes on value between 9.5 and 10.5. Okay, is this point clear? I'm trying to make, because 10 would be at the center of the rectangle. We need to add 0.5 to 10 while using the continuous distribution and subtract 0.5 from 10, and then we get our relevant interval. This is for, this expression is for non-standard normal distribution. Now we have to convert it to a standard normal distribution. For that, what we will do is 9.5 minus the mean, which is 12, by standard deviation, which is 0.219, if I'm correct. Yes, less than or equal to z. 10.5 minus 12 divided by 0.219. These values are minus 1.14 less than equal to minus 0.68. So 0.68 minus 1.14. Please look at the cumulative normal table and give me these values. Just locate minus 0.68 as a combination of values on rows and column. So you should be looking for minus 0.6 and 0.8 here. This combination, and minus 1.10 and 0.04. This combination, give me these two values. is 2.4.2483 minus, this is not 0.1271. Okay, it might be 1.1. Sorry, yeah, 1.1 and point 1271. That is correct. 0.1271. Just do the maths and get me this, the difference. It should be 0.1212. Correct me if I'm wrong. Okay, now let's look at what we have. This is the answer we got while we dealt with the discrete distribution using the concepts of the discrete distribution 0.117. And this is what we got when we approximated the discrete distribution with a continuous distribution. Okay, so we're pretty close, not that far off. Now for the exact expression of continuity correction. If you want probability, this one, x is less than x, and this is specifically for binomial. So this is the expression for cumulative binomial. This will be approximately equal to area under the normal curve to the left of x plus 0.5. Okay, whatever value that we are looking for, we have to move the point towards the right by 0.5. So here the value that we had, x took the value 10. So what we did was we moved it to the right. Let me again draw this. Okay, so if we're looking for the value that x takes on less than 10, so in terms of binomial, we're looking at areas of all these rectangles together. If we approximate this with a normal distribution, what we have to do is we have to select a value to the right of 10, that is 10.5, and select this area. It's a bit dirty now, but I think you'll get the point. Okay, so moving our reference point to the right of the value that the random variable takes by 0.5 is the continuity correction. Is it fine? Yeah. And by now you should know that whenever we have approximations, we have rules of thumb. So the rule of thumb for this approximation is, if we have n into p greater than 10 and n into q also greater than 10, that then the normal approximation to binomial distribution is acceptable. Okay, but rules of thumbs are rules of thumb. It also depends on the nature of the problem. If the nature is very severe, if the cost of error is very high, then we have to be more strict about approximation. Yeah. That is all I have for you in today's lecture. Let me stop recording.